Okay, so today we are going over I just need to, so first off there isn't a quiz today. There will be a quiz later this week. And what I want to do is I just want to talk about the data structure that I posted over the weekend. There'll probably be a quiz on it for you guys on Wednesday. So the data structure, and also I'll be posting more videos on the queue later, but the queue doesn't really come up it's a lot more straightforward to use. It's not really, you don't really use it so much in solving the puzzles we need to solve over the next couple weeks. And the homework, all the homeworks this week are kind of going to be related. They almost all use the same strategy to solve, which is using backtracking. This week we're doing something called def for search to solve a maze. Now let's go ahead and I'll go ahead and review. First off, with a maze, so first off, the data structure we went over is a stack. So what kind of data structure is a stack? Does anybody remember how you manipulate it? It's a blank in, blank out data structure. Anybody remember?
Is it first in, last out?
First in, last out. Technically, it works, right? The first thing to go into a stack will be the last thing to come out. But technically, although the book puts it down as a last in, first out data structure, the last thing to go in is going to be the first thing to come out. You can see how that works out to be pretty much the equivalent. And that's opposed to the queue, which will be, so stacks are last in, first out, right? As opposed to the queue, which we'll see is a first in, first out. In fact, I could explain the queue right here. Imagine a line. Boom, we're done. Okay, so that's what a queue is. Okay, the stack and the queue are extremely well named data structures. Computer scientists are actually really good at naming stuff. Unlike historians who name things like the 100 Years' War, which did not last 100 years, and the 7 Years' War, which did not last 7 years. So these are because they're terrible at naming things. Okay, but stacks are they're really straightforward. Imagine you have a stack of pancakes, a stack of delicious pancakes, right? If you're going to be putting more pancakes onto that stack, you're not going to be sliding them into the middle or to the bottom of the stack. When you're adding pancakes to a stack, you're going to put them on top. Otherwise, your stack of delicious pancakes is going to fall all over. Likewise, if you're removing a pancake from a stack, you're going to be taking it from the top, right? You're not going to be sliding just one single pancake out from the middle. Because, again, then you're just going to create this buttery, syrupy mess, and that's just not fun, right? So we have 4 operations for the stack, which and I built this like a linked list. So this is the equivalent of having a linked list, and the only thing you can do is add and remove from the head, which is, so you've got the push, which puts something onto the stack, right? Push puts something onto the stack. Pop removes the top item from the stack, and it also gives it back to you. So it will return the item you're removing, just like a remove method would return it. But typically, if you want to know what's on top of the stack, you don't pop it and then push it back on. Instead, you use peek, right? You peek at the top of the stack, and that'll return what's there without removing it. So push to put on, pop to remove, peek to check what's there. We don't even keep track of the size. We simply keep track of whether it's empty or not. And your book codes it up like this as empty. I like to code it up as is empty because that makes more grammatical sense for me, right? I like all my Booleans to start with an is. All my Boolean methods to start with an is word. So like is empty. So that works out pretty well. And as we'll see with the queue, all you get is I use the term, the book uses different terms than I like to use NQ, DQ, and peek as well. And then, again, is empty. So we'll just see that in the upcoming videos that Q works pretty much the same way. And so we've got this push method. So we've got the stack. All right. And it's a fairly powerful data structure, even though it's very, very limited. Because and I went over this in the first lecture, but and I may went into too much detail on it, but you can draw these things called state machines, right? Discrete finite automatas, as they're called. Discrete finite automata, right? Come on, server not found? Oh, is my wireless off? Well, that would explain it. Okay, turn on. All right, so so much for showing that off. Oh, there we go. Discrete finite automata, which are basically these little diagrams that show you, can I go from this state? If I see a 1, I'm going to go to this state. If I see another one, if I see another one, I'll go back to the state I'm in. If I see a 0, I'm going to go into this state. Basically, they're ways of moving around states. Now, regular languages and these diagrams encode the same amount of information. Okay? So one example for regular language is the regular expressions that you use to search for stuff. So any regular expression, you can kind of turn it into a diagram, actually, just like you can kind of diagram an English sentence, although that's a much more advanced language. Up on the tier of languages after that is, from your state diagram, let's see, you can go into what's called a context-free grammar, which has a non-deterministic pushdown, or which basically says that you have this machine and you have the stack. Essentially, it's a state diagram, but you have a stack at the same time. And there's all these formal mathematics as to what you can do with it. See, it uses all those fun Greek symbols to scare you off from knowing how easy they actually are, okay? They just use Greek to intimidate you. Don't worry about that. All right, and those are called context-free grammars, which basically are grammars that can have these definitions that basically saying you can replace one word with another word and these words with a syllable. And those are the kinds of things that solve the problems that I was talking about, like can you balance parentheses out? Okay, can you check if your parentheses are balanced? Now, once you add in a second stack, you can create. You actually go quite a bit far up the chain into making what's called a Turing machine. So basically, having a state diagram with 2 stacks, that gives you a Turing machine. Because 2 stacks put together, that's essentially saying I've got one stack here for everything to the left. Say I'm looking at a specific bit in a computer. Everything to the left is in the left stack. Everything to the right is in the right stack. And I can just move back and forth between the stacks to kind of seek the proper bit. And then I can switch that bit and put it on top of the stack. So once you've got 2 stacks, essentially you can start modeling a computer, which is kind of fascinating that basically 2 stacks gives you everything you need. Now that stuff is taught in like a 4,000 level course on formal automata, which is actually pretty interesting because that answers the questions of what can a computer do, right? And notice that it's basically saying, hey, here's a state of squares, and we're just simply going forward with these states. And they add these formal mathematical definitions, which again says, what can you do with a computer? And actually, are there things we can't do with the computer? And it turns out there are. But that's, again, a bit of a high level. But it's amazing that just such a simple structure can be used for these kind of things. We'll be using the simple structure for our maze program, which hopefully you've gotten a chance to take a look at. So I've given you a file which has MazeGrid solution, and you're going to want to replace that with MazeGrid panel. And what this will do, if you compile it and you run it, is that it will generate a maze. So we'll generate you a maze. I'm going to actually generate a smaller maze, something a bit easier on the eyes for these screens. So I'm just going to compile it and run it again. Right, so that's the same maze, generated by the same algorithm. These are random generally. These mazes are randomly generated, but they aren't smartly generated. They aren't a particularly well-generated maze. But my code in there is there for you to look at. Now, what I've done is that I've got these. I've marked the start at the top left corner and the exit as the bottom right corner, right over here. And your goal, as you may imagine, is to write a program that will find a route from the start of the maze to the exit of the maze. Okay. Now this maze isn't a particularly difficult one. I wanted to generate a maze in a way that was different than the way you'll have to be solving it. And the way you're going to be solving it is using a method called depth first search, which I describe as the equivalent of what you're going to do is that you're going to have essentially a lot of rope, an infinite amount of rope, and you're going to have a bunch of chalk with you, essentially. And you color the path that you're going down, and then you mark and you color the path that basically you found to be dead ends a different color. Okay. And then at the end, you're just going to be able to draw a path from. Basically, you'll just have the correct route. So if we switch this to the solution, which is what you should be seeing when you solve your code, this is your solution should look something like this. Okay. So the grayed out areas are the areas that my algorithm has visited, and the green, and it stops once it hit once it found its way to the end, right? So the green path is from the top corner to the bottom corner. Now my maze is constructed in this particular way. The way it constructs, so your solution is always going to look some weird curving diagonal thing that never really loops back on itself, because the way I generate this maze is for every square, every cell as I call it, I either choose to remove the west wall of the square or the north wall of the square. So for this guy, right, I removed his west and I removed his north. By the way, by removing his north, I also removed this guy's south, right? It's the same square, right? So anyway, let's go ahead and just briefly go over the code, but I did that in your videos anyway, so this will be just brief from me. All right, so this is your maze class. This is what you run. This is your main class to run, and it creates the maze grid panel, which holds the actual maze in it. And all I do is just set up so that when you actually hit the close button, it actually closes. The next thing we do, so next is your maze grid panel, which is where you solve the problem. So there are two methods in there. There's the solve maze, which gives you obviously that's what you have to write to solve the maze. And then you've got generate DFS maze, which is extra credit, which generates the maze using depth first search, which is the way you're going to be solving the maze. So you can use the same technique for solving maze as a way to generate a maze, and it'll generate a much more classical maze for you. So to assist you in this task, I've already written a method called Boolean, which, given a row and column, tells you, is this cell visited? Now the way it tells if it's been visited is by the color of the cell, right? Notice that I've got this cell C is equal to a maze, cell being something I wrote. And notice that the maze is an array of row by column squares called cells, right? Now the way that, so I get a cell at a particular row of column, I get its status by checking by getting the background, and I say, hey, if the cell is white or red, then it's not been visited. So I use internally cell, if it's white, which is the way, mazes are, they're just white with black walls, right? If the cell's white, then it's been unvisited. Once you visit it, you can color it any color you want. I just happen to use gray and green for my colors, okay? You can use any colors you want. But if it's white or red, I return false because I haven't been there yet. Otherwise, color it something different and I'll return true. Gen maze, all this does is that if you want to do the extra credit, this is how I generated my maze, and you'll want to use a different technique for generating your maze, but this is how I generate the maze, by removing the walls. And then when I actually run this, all it does is just set up the maze, and it creates all the cells, and then it calls the maze generator and then your maze solver. Okay. Now the maze solver, I set it up for you with giving you a stack, and in the write-up, I give you the actual algorithm you want to follow in the write-up. It says here's a stack to keep track of where you were, the start of the maze, the end of the maze, and color them appropriately, and then I pushed my current location on the stack. And the way you want to know is and you'll know what your current location is by just peeking at the top of the stack. And if you can go in a direction, you go in that direction and pop that new cell push that new cell onto the stack. If you need to backtrack because you hit a dead end, you color your current square appropriately and pop, and then you look at the top of your stack to see where you are now. So stack is simply to keep track of where you are in the maze. Cells are fairly straightforward, but you should know, and one way you can tell whether you can travel into a cell is whether or not there's a wall in the way, right? You also have a row and column, by the way. That keeps track of the cell's individual row and column, so that's how you can figure out where you are by just asking that cell, what cell are you? Oh, what's your row, what's your column? Otherwise, there's the only thing that's really all you need to know about it, other than seeing how I've done it with the maze generator. So it's a fairly straightforward algorithm, believe it or not, even though it looks very intimidating. The way this is called depth first search, which means that your strategy for solving this is that you explore a corridor as far as you can, and once you hit a dead end, either by looping back around on yourself or by just hitting a dead end, you start backing up until you find a new branch you can travel down that you haven't traveled down before. And so, and I go up into more detail on that in the videos. Right. So if you've got any questions about that, yes. So there is a extra credit assignment. That's due.
Okay.
So the other assignment is that's the Joseph's, not the Joseph's one, but the solitaire one is extra credit. And the reason that is that because I don't want necessarily more than one. The regular expression is kind of there as you can do at any point. So if you need extra credit points, this is your, can you just give me another assignment so I can get some more points? That's the assignment just waiting there for that. And then I just don't want more than one of those out at the point. So if you can get really close to solving it, but you don't think you can make the deadline, just speak to me. Okay? So the extra credit's there if you need. So this one's just an extra credit assignment there if you need it.
And how many points is this?
It's going to be either. So if it counts as towards your homework, then the solitaire one's going to be 10 extra credit points for your homework. So and that's just added up on top of your total, on top of everything else. So it can push you, if you submit all the assignments, it can push you over technically 100%, and that will overflow in the grade overall.